Hey there! Welcome to the last class before the midterm. Dun dun dun. I'll give you some time a little later in the class to ask questions that just on anything you want before we go to the midterm next week. And this will be the first time I've done the midterm in Canvas, so I've got to convert everything to Canvas, which is fun! Yay! Any questions before we talk about anything else in this class? Okay, I'm going to be catching up on the grading for the last couple of assignments tonight and tomorrow. So you'll be able to see those before we get to the midterm. There will be no assignment this week. The assignment this week is basically just midterm prep. And other than that, this week I plan to talk a little bit more about interfaces in depth. So let's go ahead and get started here. Okay, so we've already seen interfaces a little bit, but I want to go in a little more detail on them. Let's talk about why you might want to do an interface and what the general concept of an interface is. Sometimes in other languages, people don't get them described as well as they might. Let's say, for example, that we wanted to represent a movie script as some kind of a definition that we can cast different actors as the roles in the interface. So if I set up a interface, I'll call it the Terminator. This is a character in our movie, and we don't really care who's implementing it. I mean, ultimately, we're going to try to find somebody who fits the role best, but really what we care about is how this character interacts with other characters in the script. So I'm going to define a few little functions in here. Like he'll say, "I'll be back." He will say, "Are you Sarah Connor?" I can't remember if she has an H on the end of her name for the movie or not. And fun walk menacingly. Something like that. So this might describe our Terminator character, and any actors who want to portray the Terminator in the movie have to be willing to do these things. Let's have an interface. We'll call it Sarah Connor. I'm pretty sure it's not with an H. And of course, on the side here, I'm doing a... No, it is with an H. Okay, I did a little Google search on that. So we'll keep the H on there. I can never remember who has it as an H and who doesn't. So we will say fun scream. She does that early in the movie. And then fun say you're terminated at the end. And she's also going to run, and that'll be good. So there's some things that Sarah Connor needs to do in the script. Now that we've got these two characters defined, we can actually use them in a script. So if I defined a class called Terminator script, the Terminator script is going to have two actors cast into these roles. Now, I have to be a little careful with the word cast here because when you're talking about programming language, cast means, whoops, what was that? I don't know if everybody else heard that, but there was some kind of loud sound. I have to be a little careful with the word cast because in programming language, cast means changing the way you view a type. Oh yeah, no worries, no worries. Sometimes that happens. That was just a little in my ear. I'm like, whoa, what was that? In a programming language, cast means you're looking at an object in a different way. So you're treating it as though it's a different type. In the movie industry, casting just means somebody is agreeing to play the role. So in this Terminator script, we're going to have two actors passed in here to play the Terminator and to play Sarah Connor. And then we're going to have a little fun here called action, which is just going to actually run the script. So we're actually going to have the director yell action, and then stuff happens, and then we can have these characters interact. So we could have, let's say we start off with the Terminator saying, are you Sarah Connor? And then Sarah Connor screams, and then Sarah Connor runs, and then the Terminator goes to the police station and says, I'll be back. And maybe actually, I don't know we'll have him walk menacingly here. He could do that in any number of places. Well, he needs to do it more than once, so we'll just have him do it in several places there. And then in the end, Sarah Connor says, you're terminated, with a nice little expletive at the end there, and squishes the Terminator in the machine press. So that's basically our movie, how we're describing it. And notice that we don't have any idea who's playing these roles when we write this script. So it's very much like a movie script being written. We don't know who's going to play the roles. Now you'll notice here that Terminator and Sarah Connor are kind of squiggly. And the reason for that is it's saying that these could be private because nothing outside of the Terminator script is asking for them. Nothing is going to use them. And that's going to be true. We're going to pass in some values for these and never actually use them anywhere outside of the script. So I can just go ahead and make these private. And now, the Kotlin's happy. So from the outside, nobody can ask the Terminator script who's been cast. Once they're cast, boom, that's it. They've been cast. So now we need to have some actors audition and agree to play these roles. Some actors may be perfectly willing to play these roles and may already be a good fit for them. Others may say, no, I don't want to play it. And the way we have an actor say that they're willing to play the role is they're going to implement these interfaces. So we're going to have a class Arnold who's going to implement Terminator. And you'll notice that we get the red squiggles there saying, hey, Arnold isn't fulfilling his contract here. When you say you're implementing an interface, you are agreeing to fulfill a contract. And the contract of the Terminator requires these three functions. So Arnold has to be willing to do these three things. So what we're going to do is we're going to come over to Arnold here, and we're going to say implement members. And boom, now we have implementations of these. Now, I'm not sure if I talked about these to-do functions yet. Anyone have an idea if I talked about those yet? I don't think I did. What's really interesting, in a lot of languages, people come in and they'll put a little to-do comment to say, oh yeah, remind myself to do this later. The problem with a to-do comment is if you actually run that function, it's going to run just fine. So it's not something that is enforced by the language. The to-do function in Kotlin throws an exception if you haven't implemented that. Let's take a look at him real quick here. We'll see here that he says this is a function expression that just throws a not implemented error. And then this means if you actually run it and didn't provide that functionality, boom, your application blows up. Now, a little more interesting thing here you might have noticed when this first came up here is to-do has a type of nothing. Nothing is the subclass of everything. We have at the top of our class hierarchy any, so every class in Kotlin, if it doesn't have an explicit superclass, his superclass is any. That's just the top of the hierarchy. Nothing is at the bottom of the hierarchy. Anything can implement nothing. But what nothing means when you use it as a return type is that this function will never return successfully. It will always crash. And that gives you the capability inside here. If I put some code after this, Kotlin is smart enough to say, hey, it's not possible to get to this line. So if I float over it, it's going to say unreachable code. And that's because the to-do function, having that return type of nothing, is telling the Kotlin compiler, I will never return successfully. And so Kotlin can do a little bit of extra analysis on this and say, yeah, it's not possible to get to this line. So it's really nice to be able to use nothing as a return type for cases like this. This gives you not only that little commentary of, oh yeah, I got to remind myself to fill this in later, but in case you forgot to actually look for those reminders, this will crash if you try to call, say, I'll be back. So we're going to implement these guys now. That's a great placeholder. I'm going to put in a println I'll be back, something like that. And then for saying, are you Sarah Connor, I'm just going to go ahead and delete these other two ones here. Something like that. So that's kind of close to it. And then done, 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 something like that. So there's his little sound effect when he walks menacingly. He has his little theme that the music plays behind the scenes. So poof, now Arnold has agreed to be the Terminator. He's implemented all the things he's required to implement to be a Terminator. And we can now pass Arnold into the Terminator script when we create it. Now we got to do the same kind of thing for Linda Hamilton. So we'll create a Linda class. That's going to be a Sarah Connor. And implement those members. Again, she gets those to-do calls as defaults. I'm just going to go ahead and delete those. So we're going to println eq for her scream. And then this is before she actually became an action hero. When he first meets her, she's just a normal, ordinary person. But then later on in the movie, she becomes the big action hero. So in Terminator 2, it's like, yeah, she's a badass. So running sound, what is this? I will say footfalls. And then say you're terminated. We will put in println you're terminated with her little expletive at the end there. So now Linda Hamilton has implemented this interface. She's agreed to be in this movie. So do I have no, I don't have a main in here yet. Let's create our little main to actually do something. And in here, we need to create instances of these people and then cast them into the movie role. So I'm going to say, let's create an Arnold. And then let's create a Sarah Connor. And then let's create an instance of, oh, why is she unhappy? Oh, I'm sorry, it's a Linda. So they're just actual people. We're not going to refer to them by their roles at this point. But then when we create our Terminator script, did I call it Terminator script? I did. Okay. Let's just say script. Why is that capitalizing that? Now I actually have to pass those in there. So I'm going to say the Terminator is going to be Arnold. And then Sarah Connor is going to be Linda Hamilton. There we go. So now we've created our script. And now we can come in here and say script.action. And when we run this, hopefully we will see a wonderful performance from the two of them. There we go. So this now is the movie as we see it. These two people were cast in it, and they worked just great. Now, we're not saying that they're the only people in the world who can be cast in this role. Maybe we say class Pee-wee, for Pee-wee Herman, wants to be the Terminator. And so Pee-wee might have a little bit of a different take on the role here. And him, he has to yell it, "I'll be back!" Sorry if that was a little loud. My Pee-wee needs a little work because he likes to yell things there. And then println here, kind of whiny. Are you Sarah Connor? Okay, there he goes. Boy, my Pee-wee needs a lot of work. I should really pick an actor I can do the voice for. This is going to be la 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 la. Okay, so he's going to say la la while he's walking menacingly. So very, very different take on the role, but he has agreed to play the role. So we can use him, but now we have a choice. Do we want to use an Arnold or do we want to use a Pee-wee? And when we're creating our application and putting these pieces together, we will probably choose one that we think is a better fit. That doesn't mean that other things couldn't be used. So, we could come down here and then have, let's just actually call this one script 1. And then we'll come down here and call this one script 2. And instead of Arnold, let's create a Pee-wee up here. And we'll come down here and pass Pee-wee in. And just as a by the way, if you haven't seen Pee-wee's Big Adventure, make an effort to watch that movie. It's absolutely hilarious. I ended up accidentally watching it at the movie theater because we were going to see Rocky Horror for a midnight show. And they had been running Rocky Horror for a midnight show forever, but they stopped. And when we got to the theater, it was no longer Rocky Horror. So we decided, okay, what else is showing? And Pee-wee's Big Adventure was showing, and oh my God, that was a fun movie. I think the same thing happened to us with Bill and Ted for some other movie. So we'll see here that the movie has a little bit of a different characteristic to it here. He's going la 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 all the time. You're terminated. Everything works out, but it might not have been as good a movie as if we had Arnold in the role. Okay, any questions so far? Okay, now let's think about these particular actors, Arnold, Linda, and Pee-wee. There's really only one of those. You're never going to create a second Arnold. You're never going to create a second Linda. You're never going to create a second Pee-wee. There is a single actor for each of those. And as it is right now, we could create any number of Arnolds that we want to. We really don't need to because they're always going to be acting the same way. Arnold is a singular instance. There's only one of them that ever is going to apply. So I'm going to copy that and go to my next file here. Let's change this up a little bit here. We're going to still keep the interfaces, but we're going to tweak the definition of Arnold. We only ever need one of those. So I'm going to change him to be an object. That creates a single instance of a class. It still acts as though it was created from a class. You still talk to it just like a class, but you just don't create an instance of it. Arnold is the one and only Arnold, and he's agreed to implement Terminator. So objects can implement any number of interfaces. They can extend abstract classes. They can, if you want, not even have a definition of a supertype. It could just be object Arnold and a bunch of functions. The thing, if you did that, you wouldn't be able to use Arnold as a Terminator. So we'll keep him as a Terminator here. And we can do the same kind of thing here with Pee-wee and Linda. And now watch what happens in our main here. Our main gets very, very upset when we try to actually create instances of these. And so we don't. We just get rid of that. And instead, we just reference those objects. Like that. So if you ever need a single instance of something, you can do this. Now, sometimes people say the singleton pattern is an anti-pattern. There are valid uses for it here and there. Just try not to overuse it. In Kotlin, it's baked into the language. So if you actually have a good reason to use it, if the modeling of something makes sense this way, where there's really only ever going to be one way you're implementing something, feel free to do this. And so now when I run this, I'll still get the same type of results, but my code is actually a little bit simpler here because I never need to create another one of these Pee-wees. Okay, any questions on that so far? Okay, so the next place I'm going to take this, we've seen these object definitions. Sometimes it's useful to have the object definition attached to a class itself. So if we have, let's say, a class person, and let's give him a name, and let's Give them an age as well. It's going to be an int. And we might have something, actually, let's go back with the first name and last name separation here. And then we can have a property that we're defining in here that's a derived property like we've talked about in the past. This one here could be full name, and his getter is just last name, oops, first name and last name. And I'm going to put a little comment here. Don't use a definition like this of full name in real life, kind of similar to how you might not want to have a full address printout. The reason is that different countries have different ways of organizing information. So you don't want to kind of hard code this as every person has first name, last name as their full name. There may be different ways of formatting that as a common way of doing the full name. Similar for addresses, don't do that. I'm just doing it as a simple derived property for this example. Okay. Now, sometimes you're going to have data that represents a person, but is something that's not really specific to a given instance of a person. What we can do for that is we can have an object that we attach to all people that any person can get a hold of, call functions, look at data, and so on. We don't need to create a separate instance of that object every time. Let's say as a simple example here, maybe what we want to have here is a little object definition, and we call it a companion object that might keep track of how many people we've created. So inside here, we might have a var number of people, starting off at 0. And then anytime a person's created, we can say number of people plus plus. Now we have to be careful to make this thread safe. We'll talk about that after the midterms at some point there. Because if you create multiple people at the same time, we could end up getting some really weird situations with this. Just as a little hint to what's going on there, the problem is plus plus is not atomic. And what I mean by that is this plus plus operator, and this also is similar in Java, by the way, this plus plus operator has to fetch the current value, update that value, and then store that value again inside the variable. That's 3 separate operations. If multiple calls to that are happening at the same time, you could end up having all of those calls fetch the value, let's say that there were 4 people created before, so they'd all create this 4, they all increment, and then they all set, and now you might have 7 people, but it only counts 4. We're not going to worry about how to do that right now. I just want to mention that this is something, if you see this in code, be really, really careful, because there's only one instance of this object that has number of people inside of it. Now, with this variable, we can now access that by talking to the person type itself as opposed to an instance of a person. So if I came in here and I said, give me my main, and I will say println person dot number of people. Note that I'm just talking to the class in the class type itself. And then if I say val p1 equals person, and I'm just going to use the same data for all these people for now. I need an age in there. Oops. Sometimes that pop-up drives me nuts. And let's just actually print out, after each of these people is created, how many people there are. So when I run this, boom, I get all of my information printed out there. Pretty simple. So that's one type of place where we can keep track of some data across all person classes. And that data is accessible inside the person class itself. I'm not super thrilled with this definition because of the setter being accessible inside of here. If assuming you have control of the person class yourself and don't do anything stupid with number of people, it can work. You just have to, the problem is that this can be accessed anywhere inside a person. So somebody else in a different function might mess with it, and that could cause some issues. Other things you might want to do with this is having a place for common constants that the person can get to. So what I can do is I can say const val, and let's say maybe we want to have a default first name. And by default, everyone shall be named Scott. And so we can now use that up here inside the person class. And this is scoped to this person class. And you might want to make this particular one private if nobody outside the class needs to use it. So we could use it inside the class, but anybody outside wouldn't be able to see the default first name. It just doesn't exist. If, however, you do want this to be something that's visible outside, you could use it just as a public constant there instead of a private constant. Now, let's talk about the const for a minute here. What exactly is a const? We know that val means that there's no setter generated for it, but a const is something special that when you add that, the compiler can use this directly. So in this case, the compiler creates this default first name as Scott, and because it's a constant, he can say, you know, I don't really need to have a separate data holder for Scott. I can just bake that into my class executable as a string that everybody can access. And where we access it, it actually just replaces it with the string directly at compile time. So that's an optimization that can happen there. And we can do that also for different numbers. So maybe default age. Maybe we'll say default age is 10. So you can come up here and say equals default age, boom. And oops, what does he not like there? Oh, sorry, I put that in the wrong spot. There we go. Thank you, compiler, for saving me from myself there. So now we have our default age being passed in, and we can keep track of that down here. Now, the reason we might want to put these in a companion object, we could put these at the top of the file or somewhere else. The difference is scoping. If I put it out here, anybody, anywhere in my application can use this as just default age by itself. Technically, it's called main kt.default age, but from the Kotlin point of view, it's just a top-level declaration anybody can get to. Now, if I made it private, anybody in the file can get it, but anybody outside this file can't. But that means that if I had, you know, another class here, maybe a dog class, if he had an age, he could use it too. If you really want to restrict it to being used in a certain place, that's when you can make it private inside of a companion object. And then it's something useful inside of the person itself. So let me actually put a couple things up here. So if I made it like this, maybe we'll say default age 1, default age 2. Any type in the compilation unit, actually outside the compilation user can use it as well. Any type can use this. Only, let's say any expression inside or outside the file. Only expressions in, oh wow, it's going to be one of those times, in this file can use this. And then down here, if I made this private, actually, let me do the same thing with the default age. I'll call default age 3. Only person can use it. Any expression can use this. Must be qualified. And this is kind of the key here. When you put something in a companion object, let me kill him. The key is really when it's in a companion object, you must qualify that for usage. So what we're doing is we're putting a namespace on something. We're setting it up so that you know what it belongs to, as opposed to this guy just kind of floating out here, or this one here, that anybody in the world can use. So companion objects are particularly useful for defining constants and scoping things like that. Now, inside of the companion object, yes, you can have variables, you can have constants and things like that, but you can also have functions that the companion object uses to do things. One type of function you might want to do here is creating something that looks like a constructor. So if I say operator fun, I think this is how I do it, create person. Is that what I want to do? No, I just didn't say create person. What am I doing? Then I can have that return a person. And then that's going to do some setup, maybe using some of these constants here. So if you call create person by itself, I would say return person, default first name, and maybe some last name. Yeah, I'll put a last name in here. Why not? And then the default age, something like that. So this now kind of looks like a constructor. And actually, let me just say person. Why not? Note that I can actually call this function the same name as the type. It's still a different function because I'm overloading it. I'm using a different set of parameters on it from the primary constructor that's available. And there's no alternative constructors inside of here. So inside this, I could now use this person function to create things. But it's a little awkward, huh? So I could say, let's come down here. Oh, come on. What was I at? So P5. Note that that doesn't work because I don't have my scoping set there. So I can come in here and say person.person, and that's just super awkward. So what we can do is we can use a special type of function. That's where the operator came in that I was trying to do before. If I said operator fun invoke and said last name string, I think this is what I wanted to do. Yeah. I got a couple different thoughts tied up in my head on that one. I can create this function called invoke. And invoke is the operator that acts like parameter list paren. So if I did this, now I can come down here and just directly say person. And now it feels like an alternative constructor that I've set up here. Oop, got one more person coming in, I'll admit. So it feels like now a constructor, and it looks like a constructor. And because of this, you really want to be careful on how you use this if you're using it inside of a companion object there, because it really kind of feels like object creation. You only want to use this for object creation in this case. Now this invoke function is also the default function name that you're using when you're defining a functional type. Before I move on there, are there any questions on anything I've covered on this one so far? This is actually a special name in Kotlin. It's an operator overload. So just like we did before with operator fun get, where we have like a some value being used as an index here maybe, and returning a value. Just like we had this, and I'm just going to hard code that for the second. And we'll say val p0 equals person, blip, 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 10. Why not? And then we could say p0 sub 10. We'll println that. So just like we could override the get function, which is the operator overload for this index syntax, invoke is an override for this parenthesis syntax here. And so the thing that's nice about invoke is that you can explicitly use it if you wanted to. So we can come in here and say p7.invoke. So you could use it explicitly, or you can use it in operator format by using those parens. And there's some places where this is actually super, super useful. Let's think about what would happen if we define this function in something that's nullable. Now, companion object can never be nullable just by default. It just isn't. But if we were defining this operator fun invoke inside of an object that can be nullable, like let's say this get guy, for example, this person can be used in a nullable context somewhere. So what we could do, I'm going to say awkward side discussion, awkward because a person wouldn't have this. But it's useful to be able to say, just talking about operator overloading here. So down here, the thing that's really nice about having that have a name in Kotlin is that you can reference it if something's nullable. So if I said p0 : person ? And let's just actually make that a var so that the compile is going to be okay with that. And now he's going to complain that you're never modifying it. Notice how if this is nullable, I now get a syntax error here. And the thing is that I haven't checked for nullability. And I can't use that null safe accessor, the ? Dot, in this case, because I need to have a function name after that dot. So here's where having these, the brackets or other types of operators, the invoke, for example, is something that you would need to have the function name for. So something like this, if I wanted this to be nullable and wanted to use the null safe accessor, then I'd have to actually call out the real name itself. And invoke is useful that way as well. So if I came down here, actually, I don't think I can define, well, no, I can define invoke as long as the parameter list isn't the same. Let me see what happens if I use the same parameter list. I get the feeling it's not going to let me do that. At least I would hope it's not going to let me do that. Well, first of all, I can't use vals there. Interesting. Oh, return type. I'm surprised it lets me do that, because this seems to me to be a conflict with the constructor, and I'm not really sure what's going to get called there. Is this going to be ambiguous? Oh, wow, that's weird. Okay, so now I just got to try something. I want to see what's getting called there. I would have thought the compiler would have stopped me here, because from a syntax point of view, this is ambiguous, right? Is it calling invoke, or is it? Oh, no, it's not ambiguous, because this is actually being called on a person instance. Versus if I had this one do it, I bet here if I did it, that's going to be ambiguous, because that's on the class. Oh, is it going to let me do that? That's interesting. See, I'm really wondering which one's going to get called now. Okay, so let me try this out, because inquiring minds want to know. Let's come here. If this works, I might have to file a bug report. So here, the companion object, you're going to have to, this invoke, you can call just by saying person. So which one of these is going to be called? Let's find out. Println pp. Did I make that a data object or data class? Let's make it a data class. Okay, and let's see what happens when I run that now. It's going to hit the invoke. No, it hit the primary constructor. Ooh, that's interesting. I got to look into that. I think that should be reported as a ambiguity there, because it's ambiguous whether the companion object should be triggering that. Interesting. Okay, making a quick note here, file bug report. I wonder if that's intentional behavior or not. It may just be the case of nobody thought to do something that reckless. Because I'm being reckless, what can I say? Just doing some wacky stuff there. That's very interesting. Anyway, this one down here would have to be called on the actual person itself. But having the ability to have that invoke lets us use functional types and still be able to call them if they're nullable. So a little more direct example of that, if I said funfoo, and in that definition, I'm passing in a sum function, which is going to take a string, and it's going to return an int, let's say. And then inside here, I'm going to call sum function, passing in Scott, and I'll println the result of that, something like that. So if I have that little foo function, if I have right now if I call it, I know that some function is non-null. There's no way for it's not nullable at this point here. So I can use it by just saying sum function paren. Let me actually rename him to be sum function 1. There we go. I'm going to make a sum function 2, but let's say that I want it to possibly be null. Now the question here, first of all, is how do I specify that? In order to say that this is a nullable function coming in, I need to surround the type with parentheses to kind of keep it together. Because if I just put a question mark on the end, this is defining a function that's not null. He takes a string and he returns a nullable int. I want to say the entire type, so that actual function being passed in is nullable. So I'd need to surround the functional type with parens to keep it together, and then put the question mark after. So in this case, some function can be null, some function 2, and this one, some function 1 cannot be null. And I'm actually I'll put in that middle example just to keep that in here for the second, just so that you know what the difference is here. So some function cannot be null, and we'll say takes a string, returns nullable int. And then this one, we're going to say he takes a string and returns an int. And this one, same type of thing. So do these function definitions sound comfortable to everybody? Any questions on what I've just written there and what they mean? Okay, I'll take that as a no. And by the way, if those make sense to you, you're going to do great in Kotlin. I mean, once you're comfortable with writing code like that, you're going to have no problem with this language whatsoever. This, I think, is probably one of the hardest things in the language, is just getting used to nullability, getting used to functional type definitions. Those are really the tricky parts. Okay, and so we can print this out. But watch what happens if I try to call some function 3 there. He's telling me, hey, that thing could be null, and you didn't check for it. So you need to deal with this. So notice how it says use explicit $.invoke. Now, I could do that. Don't do this. Or at least 99 point, a whole bunch of nines. There may be a case, very, very, very rare case, where it makes sense for you to say, okay, hey, listen, compiler, I know for a fact at this point in time, this cannot possibly be null. Be really, really careful on that. You generally don't want to do that because a lot of times there's going to be paths that can change over time. And if somebody tweaks a little code somewhere, this assertion that you made here, that's called a non-null assertion, this assertion that you've made to the compiler might not hold true. It's always best to be safe on it. So the safe way of doing that is using the ? Dot, right? And because of that, that's where you need to have the actual function name, and in this case, invoke. So when these functional types are created, it creates an object that has a function called invoke, which is the function that you're defining here. So that's really what this is doing. This guy is an object. He has an invoke function, and you're going to call that invoke function. Does that make some sense? So this is something you're going to have to do once in a while. It's a little unfortunate. I wish they had a slightly better syntax on this. But as long as you understand that when you're defining these functional types, it's actually an object that has a function, or it's treated like an object that has a function. Just depends on how Kotlin's implementing behind the scenes. Okay, any questions on that? Okay, so let's see, it's the next thing I wanted to talk about on this page before I move on. If you want to change that from invoke to something else, what we can do, what else I've been defining inside of here? Okay, what you can do is you can define something, an interface with a certain function in it. I'll say interface. Let's say that we want to represent an interface that somebody, some object would call to tell you that the sun has risen. So I could define a sun listener interface with a fun sun rose that returns a, or let's say it takes a, well, no, we're not going to take anything. Maybe it'll just return a string that's like a nice little happy message when the sun rises. So using this sun listener interface, I can define a fun report sun status function. And inside of here, well, I'll give them a listener here. I could define a sun listener like that, and inside this function say sun listener dot sun rose, boom. If this were nullable, I could say ? Dot sun rose. So yeah, it's kind of interesting there. What was my point here? I had a point here and I'm blanking on what it was. Type alias. Type alias is a little different. Be careful, but a type alias itself lets you define just a name for a functional type, just for convenience. So like, instead of writing this out every time, you could use a name for it. Personally, I'm not a fan of that. I think it causes more confusion than anything. So I was trying to work my way into where you could replace this invoke. So in this case, obviously, we're not calling it invoke, we're calling it sunrose inside here. This was going to be something related to functional interfaces, and I'm blanking on it. I think it's, I think I was thinking of this with regard to cross Java compatibility, and I really didn't want to talk about that right now. So I'm going to just magically erase this and pretend it never happened. And we will talk about that when we talk about Java compatibility a little bit later. So forget I mentioned anything. I almost went down another rabbit hole, and you know what happens when I do that. Okay, so any questions on this stuff that we're talking about here before I move on? Okay, good, 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 good. So let's go to a new file here. And we were talking about interfaces and companion objects. We did all those. Let's talk about mixing in different sets of functionality. In Java and in Kotlin, you can only have a single supertype. Oh, I'm sorry. Was somebody trying to ask a question? Or nope, I guess not. Um, can you hear me? Can you hear me okay? I can't make out what you're saying. Did you have a question, or was that just some background noise? Okay, well, if there's a question I can't hear you, if you could type it into the meeting chat, I can do that. Okay. Um, so sometimes you might want to have multiple superclasses. You can't do that in Java or Kotlin. So if I had something like class mammal, and maybe I'll just make it an abstract class because that makes more sense. And then I have a class human, extending mammal, and maybe I also want to have a class, I don't know, doctor. I can't have human extend both mammal and doctor. It just won't work. I can only have a single supertype. Single superclass only. So I'm going to comment him out. But maybe I do want to pull in that functionality. What you want to do when you're thinking about classes, you want to always think of it as the is-a relationship. Whereas an interface, it's a can-do relationship. And the difference between these is for classes, you're basically classifying your hierarchy. And it has to be a very strictly single supertype hierarchy. With an interface, you're describing traits, things that ways you can communicate with it. And you can have any number of interfaces saying what you want to do. The problem is maybe you don't have implementations of those things. So let's see what happens if we change these to an interface doctor. And maybe he has a fun prescribe, I don't know, medication. And whoops, let's comment those guys out there. There we go. And then maybe we want to still have our mammal and then human situation there. So maybe I have an abstract class mammal and then a class human who extends mammal. Note the parentheses there. You have to put a constructor call for the superclass. But for doctor, being my interface, I can just go ahead and put the interface name there. There's nothing to call as a supertype on that. But note now, my human has to do all the work. He has to implement how do I prescribe medication. So I'll come up in here and say implement him. Println, scribble on paper. There we go. So now we have a complete human interface there. But the problem is every time I want to implement this, maybe I have a cat who's a doctor. Scribble on paper, eat it. And maybe I want to have a dog. Well, let's say they're all actually doing the same thing. I'm not going to have meat. I'm just going to have them do the same thing. So then a dog is going to do the same thing. He's going to scribble on paper. So you notice that we have to actually re-implement the same thing over and over and over again. Now, one thing that we can do to get around that is to use something called default functions. So if I come in here and I define a doctor2, and we'll put a mammal2, human2, doctor2, and we'll do the same thing over here, cat2, mammal2, doctor2, mammal2, dog2, something like that. So if I came up in here, I could actually have a default implementation for this. I can still override it, but I could have a println scribble on paper. And then boom, 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 boom. But maybe the dog wants to do things a little differently. So he can change his behavior, but I can inherit this default behavior inside these other objects. I can even define data inside here, but notice how when I define the data, it says I have to implement it. So what could be interesting in here is maybe we scribble on paper $X, and then, whoops, we override X, kind of like that. And maybe we override X to be a little different over here, and so on. And then the mammal has to implement them as well. Or the dog has to implement as well. I'll make him 30. Why not? So notice that we have some defaulted functionality here that uses some abstract features. Now, if I try to define something as a concrete implementation, no can do. You can't do that with data. So data cannot be defaulted. I believe, let's see if this is right. I don't know if I've tried this before. I think you can override the getter, or you can default the getter. No. Yeah, you can't. You just can't have. That's interesting because I'm not referencing field, but he's saying here property and interface can't have a backing field. He's basically just trying to say you can't have. Because it's a var. Duh. Let's make him a val. See if that'll work. There we go. Okay, so you can set that. You just can't have a backing field on the data. So no vars, but you can have some vals if you want to have vals. And then this val could be overridden as well. Well, I mean, I should say you can have a var if you don't need a backing field. So properties without backing fields are okay. And notice how nobody needs to define z, but if you wanted to, you could override z. And we could use z inside of here as well. So one way that you can provide some mix-in functionality is to use default functions properties. So you can do something kind of like that. And this now allows me to pull in functionality from multiple places. I'm pulling in the functionality from mammal2, and I'm pulling in the functionality from doctor2. And then I override the pieces that I care about. So if you're going to have some really common functionality, you can do some things like this. There are limitations. You can't have backing fields. You'd have to actually override those yourself. So if there was a var up here, you have to actually override X inside each of your implementers. But this is one approach to using a mix-in type capability, which allows you to pull in functionality from multiple places. If your common functionality is simple enough, and you don't mind overriding things like any properties that are involved that require backing fields, then this is actually a fairly decent solution. You can pull in, again, this guy in particular, he's pulling in a lot of functionality from both of these guys. But keep in mind, you still only have that one is-a relationship. A cat is a mammal. Cat can do everything a doctor's required to do. So it's a can-do type of relationship. Questions so far? Now, what if we wanted to be even smarter about this? What if we wanted to actually have some default functionality for the variables themselves? Let's create a new one over in here. If you remember from when we were defining our list, we had something, kind of like data class my list, and we did something kind of like, my list is going to implement list. I'll say it's a list of strings for now. We'll talk about generics after the midterm. We're describing that we have to implement a list. And normally what we'd have to do here is create all the functions of list, which in this case, there's quite a few of them. So if I came into here, you'll see there's a bunch of functions. And then inside of here, we'd have to implement how all these work. Well, the first thing, actually, I call it a data class. Just call it a normal class like that. So would need to implement everything. And so this could be very messy. We have a lot of implementations. We'd have to put all the implementation details and so on. The next way we could approach this is if we said class myList2 implements list of string. The next approach here is to create our own delegation for things. So we'll create some object that we're going to let do the real work for us, and we can delegate some functionality to it. So in this particular case, what I'm going to do is create a private val real list equals mutable list of strings, and boom. So now inside of this class, I have a little guy who's going to help me out. He's going to do the work for me, and I'm going to delegate to him. So when I come into here and say implement methods, now all I do is say the getter here equals real list dot size. This guy here returns real list dot get at the index. This guy equals real list dot is empty. This guy equals real list dot iterator. Real list dot list iterator. Thank God for code completion. And then this one is going to be real list dot list iterator passing in the index equals real list dot sublist. And boy, this gets tedious, doesn't it? But this is typically how you do delegation. So real list dot last index of element. We're almost done. Real list dot index of element. Real list dot contains all elements, and real list dot contains element. And there we go. So this is a very strict delegation. We're letting some other object do the work for us. So I'm going to say explicit delegation. And as we've written it here, it feels very redundant. In this particular case, what is he going to be happy about here? Oh, it should be replaced with indexing. He wants us to use because it's an operator, we can use the indexing operator there. Okay. In this particular case, we're not adding any value. We're just strictly delegating to something else. But maybe this object is more than just a list. Maybe there's other functionality. So we could have, maybe there's this list functionality. Maybe there's some other interface that we want to implement. We could add that other interface here and do other things, giving us that mix-in value. But there's a much easier way to do this. Let me say explicit delegation functions. I'll put there. So instead of doing that, if we're just going to delegate to another object, we could do something like class mylist3 taking in the real list. Oops. And I'm going to make him private because we don't ever want to expose him. And we're just going to say list string by, actually, I think I can just say mutable list of string. I think that works. Yeah, there we go. So now this is actually using Kotlin delegation, say Kotlin interface delegation. So what this guy's going to do for us is it creates a list and all delegation functions. So it really strips down the work that we need to do here. We don't need to specify these. If this is the intended behavior, just passing through those interface functions, we can just go ahead and say, okay, create the thing that we want to delegate to, and then create all those delegation functions for us automatically. Does exactly the same kind of thing. But if you want to have multiple things that you are implementing, and this is kind of a silly thing here, but let's say that we wanted him to be both a list and let's create a little interface printer. And maybe this is going to have a fun print stuff. And then we'll have a class myPrinter, who's going to be a printer. Implement that interface, and we'll println hi, something like that. So what we could do is we could also make this guy a printer by saying printer by myPrinter. Boom, just like that. And so this gives you another way to do mix-ins. We're basically pulling these pieces together and delegating to other objects. So this has all the print methods, this has all the list methods, and this has that print stuff method. So I came into here, created my main, I could say val list equals mylist4, and then I could say list add 20. Oh, I didn't, well, see, that's kind of silly. Let's make that be mutable list. There we go. And it's strings. And then I could also say list dot print stuff, and it'll do the functionality from both of those interfaces. So that's kind of cool there. So this allows us to mix in functionality. And note here that in this particular case, I'm not defining any supertype. The supertype of mylist4 is any. All I'm doing is saying that mylist4 agrees to do everything that a mutable list does and agrees to do everything that a printer does, but I'm just going to let some common implementation take care of that. And this is super powerful. You don't have to write all this gobbledygook like this. The number of times I had to write this kind of code in Java was ridiculous. Now let's think about if we have an existing list and we want to try to interact with it, maybe in slightly different ways. Well, or maybe we want to, instead of creating these, let's just do the next step B. Instead of creating these explicit objects here, we want to pass in the existing objects. So in a case like that, I could say class mylist4, and inside of there, pass in, let's make it private, val real list, and he's going to be a list of strings. And I'm just going to do the strings one for right now. But I want to have us implement strings by real list. And what is he unhappy about here? Oh, I already had a 4. Let's make it a 5. There we go. So in this particular example, delegation to an existing object, I'm going to say instance. Rather, you could use Kotlin objects for this, but this is just an example of I already have a real list. I'm just going to create one. So this particular example, I might say val existing list equals mutable list of a, something like that. And then I could say val my list 5 equals my list 5, passing in that existing list, and boom, now I can work with it. Now in this particular example, it doesn't really do anything interesting. There's no value add here. Where it becomes valuable is when we tweak the functionality. And so if we said something like class mylist5, and inside of here, we have that real list coming in, and we're going to implement, well, let me change this to be mutable list because that's what I meant to be. Maybe what we want to do is set it up so that once you've created this, you're not adding stuff to this guy directly. So I could restrict what we're seeing here. Oops, this is going to be 6. I could do something like this. Whoops, I want that to be a mutable list there as well. There we go. So in this particular example, maybe we want to restrict the type. And this is where we had the example that I think I sent in an announcement of where I'm changing the type of a mutable list into just a read-only list. And so this wrapper is going to prevent anybody who has a handle to this wrapper from using the mutation functions in the real list. So maybe you have some code that's managing that real list internally and then exposes it to the outside world as this locked down list. Let me call it that and say locked down list. And let's say that we have something, I'm just going to call it a model. And the model is going to be something that keeps track of data for some kind of an application that we're dealing with. And inside this model, I have val real list equals mutable list of, actually, let's just say it's an empty list to start with. So we'll go like this. And then maybe what we want to do is only let it be mutable inside of this model. Nothing outside the model should use it. If I define it as I have it right now, anybody can say model.realList.add and add stuff to it. I want to prevent that. So the first thing I need to do is make this sucker private. So this means that the only people who can touch realList itself is the model. And because my lockdown list also defines it as private, nobody can take a lockdown list that happens to have a real list in it and get to the real list to modify it. So then the next thing is I want to expose it as this lockdown list. So now I'm going to say val lockdown list equals lockdown list wrapping the real list. So all I've done in this case is created what's called an adapter, which changes the type. So we're using the adapter pattern. Changes the type of a wrapped object. So we have some type in here. We're exposing it as a different type. And this is one place where an adapter is super useful. In this case, it's a very simple adaptation. We're just saying only define the functions that are the read-only functions. And so now using this model, anybody who defines this model, I can come down here, I can say val model equals model. I can only say model sub 10, for example. Oops, model dot lockdown list sub 10 to get that. I can't say model lockdown list sub 10 equals some value. I don't have any of the mutation functions. Whoops, I was in the wrong spot there. So that won't work. So this is one place where it's super useful. And maybe this model has a fun add stuff. And maybe I'll do a var arg stuff, which is going to be, we'll say items, which is going to be strings. And then I could say items for each real list dot add it. So I'm now controlling how things get added into this. And this is something that's very, very common when you're defining models for user interfaces, for example. The user interface, you only want to see the read-only view of things, but then ask the model to do additions or ask the model to make changes. So in a case like this, I could ask the model to add stuff, A, B, C, but they can't change it, they can't remove things. All they can do is what I'm providing because the model is in complete control of this. So this is a nice real life type situation here where we have a base property and a derived property that are being used to change the type of something. Now, a lot of times when you hear the adapter pattern, a lot of times it's being used for a much bigger change in type. So maybe you have some data that's represented as a binary tree, and you want to represent it as a J tree in Swing. In Swing, the J tree has a very specific interface for how you access the data. And that interface is different than your traditional binary tree interface. So an adapter there would be a little thin object that sits on top of that binary tree, takes the binary tree as the real data, and then interprets it. So when the questions are asked from JTree to be able to get the children from a certain node, we interpret that as get left or get right as appropriate in a binary tree. So that's a much more traditional adapter that you would see there. And before we take a break, one more little one I want to say in here. We can, when we're defining these guys, tweak the data as well. You can override whichever functions you want. And that typically falls into a decorator pattern. So if we're trying to change parameters or return types, return values, I'm going to put in here, whoops, come here. So if I'm having the same interface, but I just want to change the parameters of the return types, this is called the decorator pattern. And this might look like a class myList. What are we up to, 7 now? No, 6 at this point still. So it's myList 6. So in this case, we're going to pass in that one that we want to wrap. So private val real list. It's going to be a mutable list. And maybe we want to expose it at the exact same type, but we just want to tweak some of the behavior. By real list. So far we don't have to implement anything. Right now we have that direct delegation. But if we want to tweak some things, so let's say when things are added, we want to just put like the letter X on either side of the things that we're adding. I could override the add function. And in this case, I'd want to override all these ones, but I'm just going to override the base add function here to say real list dot add X $element X. Now notice, and this is one of those cases when we're using our dollar syntax, it looks to Kotlin like the variable we're trying to refer to is element X. So, and that creates the Powerpuff Girls, right? So it was chemical X created the Powerpuff Girls. So in this case here, I'm going to say return real list add blah, blah, blah. So I'm now tweaking the behavior. And with a decorator, you're typically going to tweak parameters coming in. You might tweak return values coming out. So this is a simple decorator here this one tweaks parameters to .add. So now if I came in here, and let's say, I'm going to go ahead and put this in my model so it's a little, it's basically kind of hidden here. So I'm going to say real list 2, and this is going to be my list 6, I think, was the one I called it. So we'll say my list 6. Again, it's a base property and derived property pair here. We're creating the real storage and hiding it from the world inside this model. We're exposing it as a mylist6. So then the outside, people have no way to avoid that overridden method. So if I come into here, the mylist6 has all the mutators. So I can call that add, but the behavior is going to change on it. So if I come into here, I can say model.mylist6.add, passing in not x, let's call it Scott. And then if I do a println model.mylist6, let's see what that does. Oops. Yeah, that would definitely be a problem. Oop. Let's get him out of there. This line here is definitely a problem because, there's no elements in the list there. Let's try running it again. And we're printing this guy. Note that mylist6 is not a data class, so he doesn't define that toString. We need to deal with that. If I came up here and I made this a data class, it would print out in its report real list equals under there. But I don't want to do that. I want to actually delegate those toString and things like that. So if I define my toString, I'm just going to have it be equals real list toString. Pretty simple there. And I'm probably going to want to do the same kind of things for hash code. Generally, you want to implement these 3 together. Real list.hashcode and equals. Real list.equals other. And yeah, it's going to say it wants me to replace that with equal. That's fine. These 2 ones, if you ever override one of them, you have to override the other one. They have to be completely consistent with each other. If they're not, you can get some really bad behavior if you try to put this object into a hash table or a hash map. This one, generally you'll implement them with the other 2, but you could just implement on its own. And so now if I run this, I'm going to get a much better result. It's going to look like I'm really printing that. And hey, take a look. Scott got those X's put around him because I changed that behavior using the decorator. Now, this stuff, if you haven't done design patterns before, I'm going to pull these up once in a while because I loved teaching design patterns. I haven't taught it in a while, and I miss it. But it's not just for me. It's like I love getting these ideas in people's heads. Decorators and adapters are 2 of the most important patterns that you'll see out of the Gang of 4 design patterns book. And it's well worth knowing them and actually seeing some realistic scenarios here. And having this model with these pairs of properties and how we're adapting or decorating is huge. Take advantage of this when you're doing things, because then we can hide the real data and tweak it to our heart's desire. So we can adapt it, or we can decorate it, change the behavior, or reinterpret the interfaces, which is really what the adapter pattern does. Okay. Any questions on that? And I'll probably show a couple little other examples of adapter and decorator at some point. But this is a really common pattern you're going to see, especially if you have some kind of a model that controls your data, because we're really giving control here. And that's the big thing we want to do with our model and with these types of exposure via base and derived properties. Okay, so with that, let's go ahead and take a break. It is 8:46. Let's say well, it's 8:47 now, so we missed it. No break. No, it's 8:47. We'll start back up at 8:57. So at this point, I would like to ask, does anybody have any questions on anything we've covered in the term so far? We are having the midterm next week, and let me just talk just very briefly about that. The types of questions I like on that. I'm taking a look at the implementation over the weekend on it. The type of questions I like are short answers, basically. So where you type stuff in yourself, multiple choice. So there'll be some options, and you choose either one of them, or there could be multi-choice ones where you have to say which ones are valid. Typically, what you'll see is you'll see like a little code sample, and then it'll ask you some questions about the code sample. Things like what are possible valid outputs, um, and yeah, there was one other thing I was thinking along those lines. Um, then there'll also be one or two longer essay type questions, which are basically where you're going to write some code. Um, when you're writing the code, it's okay to use IntelliJ to try things out and then copy the code over, or you can just go ahead and type the code in. The code doesn't have to be perfect. I mean, if there's little syntax problems here and there, don't worry about it. If it's completely off, then yeah, I'll take off for it. But in general, the thing that I'm looking for is did you have the general idea? Maybe you missed a paren here or there. It's not that big a deal. But again, if you want, you can go ahead and use IntelliJ to do to write up things and try it out. Just if make you feel more comfortable on it. Um, and that's pretty much it, the types of stuff that'll happen. So there'll be one or two coding questions, um, several multiple choice, a few short answer type questions. So I might ask you something like, what are the three tenets of object-oriented programming? And just brief answer is really all I'm looking for. Just enough to let me know that you get the concept. Um, so anything that we've covered that you want me to talk about a little bit more before we have the exam next week? Of course, if you all feel perfectly confident with all the content, then you'll be do great on the assignment or do great on the homework. Um, but I would advise the big advice I would give is take a look at all the samples, make sure you understand what the samples are actually doing. Um, if there's parts where you look at a sample and something you're kind of scratching your head, take a look at the lecture again. And I will have office hours on Monday night, so feel free. Yes, you can use notes. You can use anything you want. You can use notes. You can look on the internet. The idea here is that it's going to be an online exam, um, but the more you're familiar with the concepts, the easier it's going to be to get it done on time. It'll be a 2-hour exam. Okay, and it will cover everything up to the break today. So everything from the first class through the break today. Anything else that I talk about after the break here won't be on the midterm. Of course, me saying that means that if somebody says, "Oh, how do you do chains of lists at this point?" then that can't be on the exam. That's not what I meant. Okay, so no questions. I will have office hours on Monday, so if you're going through your notes and things and the samples and have questions about, feel free to pop on the office hours. I'm sorry, the office hours for this class is Tuesday, right? Yeah, it's Tuesday. Monday's my Android class office hours. Okay, so I guess because we don't have any questions, what shall I cover? Let me talk about enumeration classes. Um, No, actually, I'm going to stick with interfaces for this point. So let's talk about the observer pattern. And one thing that I want to talk about when I'm talking about any of these design patterns themselves, some people interpret them as recipes. I don't interpret them as recipes. Design patterns are there for communication, oops, what did I hit? Of intent. And what I mean by that is in normal language, we come up with words that have very specific meanings. And the more you use a word with a specific meaning, as long as somebody else understands that same word, your communication is much more efficient and effective, because if you're using words that very precisely describe what you're trying to communicate, the other person can know in much more detail what you're talking about. Like if you said, I like beans or something like that. There's a couple places in there where that might be problematic. What kind of beans do you like? The word like itself is kind of general. I mean, it gives it kind of an idea of it. But if you replace it with more powerful words, like if you say, if I love beans, it communicates more effectively what you're trying to say. If you say, I tolerate beans, has a very different meaning. If you say, you know, beans are, a reasonable substance for me, that has a very different meaning to it as well. The more precise you are on the wording you're using, the better people can understand what's going on in your head. And by using design pattern terms in your comments or when you're describing something, it's going to help a maintenance programmer get into your head when they're looking at your code. And one of the most important things you can do is think about that maintenance programmer. Unless you're really planning on maintaining that same piece of code for the rest of your life, somebody else is going to have to. So if you can communicate your intent, when somebody is looking at your code and you said, hey, I use the observer pattern here, they're going to get the concept of what you were thinking. And the concept can be implemented in a bunch of different ways. But the idea here is to get them to get into your mindset. That makes it much easier for them to understand where they should make changes and how they should make those changes so that they're compatible with the original mindset that you had. It can also reduce your code quite a bit there. So observer pattern, I like to talk about this one because it's typically very interface heavy. And what we'll do inside this guy is we have something called an observable, and we have something called an observer. And just based on the word here, an observable is something that can be observed. And this is something that observes an observable and is notified when something interesting happens. Ooh, I actually had a good typing line there. So the basic idea here is you have something that you want to watch and there's some information you want to know when something happens. A very typical idea here is, you might have a button in a user interface. And we want to know when the user, oh, here we go, I'm going back again, clicks the button. To do that, we don't know when the user is going to click that. So really all we can do is we can talk to the button and say, hey, button, let me know when the user clicks something. So it's probably going to happen in a different thread. That's one thing to consider about. But basically what we do is we're going to create our user interface, create our button, attach a listener to it, an observer to it. The reason I use listener is in Java, typically this observer relationship is called a listener. That's just the terminology they use. I really wish that people would use the design pattern names. The problem with Java in particular is Java came out right around the time the design pattern book came out. So it's like, I wouldn't expect them to use the common terminology as much, but because of that, the word listener has kind of propagated quite a bit across different languages and systems. So to do this, the kind of base traditional pattern is we have an interface for the observer, and then the observable tracks the observers. So let's take a look at an example of how this might work. So we define our interface. Let's say that we're talking about an interface that represents a click on a button. I'm just going to call it button click listener. And this one is going to have a button clicked function. And so this might be a very simple way of representing this. We may want to pass a little more data inside here, like when was the button clicked, or maybe where exactly on the button it was clicked. I'm going to just wave my hands at that for the moment. You can pass whatever data you want. But for now, all we care about is just the fact that the button was clicked. Then if we have a button class, this guy is going to have some way of tracking who is interested in him. So he's going to have a little list here, button click listeners equals mutable list of button click listener. So we're just going to keep track of a little list of who wants to be reported. And we're going to keep track of them in the order that they're registered. So we'll have something kind of like a fun add button click listener. And he's going to be listener, which is a button click listener. That's going to modify our list. Something like that. And then we'll do something similar to let somebody on the outside remove a listener. Boom. And then maybe we have some functionality internal here. User clicked the button. And I'm not going to talk about how that actually was interpreted. There's going to be some communication with the user interface system that's going to listen for the mouse, figure out if the user clicked on it, and then let go while they're still inside the button. And then we're going to say, oh, hey, that means the user clicked the button. And then we're going to do something about it. So we're going to assume that there's some code somewhere in the button that handles that interpretation of the user interaction as a button click or not. If it does say that the user interpreted that, if it does interpret the user interaction as a button click, it's going to call this function. And all we need to do in here is say button click listeners for each it dot button clicked. Boom, something like that. So this is a very, very simple implementation of the observer pattern. We allow people to attach these listeners or the observers, and we notify them when something interesting happens. So if we come down and have a little main here, I'm going to, let's actually do something interesting in here. Let's say that in my init, I say, just trying to decide which way I want to go about this so that it's not super confusing. I'm going to, for right now, use the Java threads to do this. So I'm going to say thread. I want to do it that way. And so what I'm going to do here is I'm going to create an object that implements or extends, in this case, thread, and I'm just overriding the run function inside there. So this run function is actually going to sleep for, let's say, 3 seconds. And then I'm going to call user click the button. So I'm just going to pretend that after we set up our user interface, 3 seconds later, a user clicked the button on the screen. So nice, simple guy there. And actually, I need to do a .start to make him actually run. And we can just do that. So we create our thread, we start our thread. It's going to go and spin off and do things. Later on, we're going to talk about coroutines. I wanted to keep it pretty simple. You may have seen threads in Java before. We're just going to use the Java virtual machine to take care of starting another thread for us. And this will happen once the button's been created. So my main here, I'm going to say val button equals button. That's going to create our button, and it's going to start that thread. So at that point, the thread is started. We get control back. We can now do other things while the thread is waiting for those 3 seconds. I'm going to say button dot add button click listener object button click listener, and we need to implement that functionality, just kind of like that. And then in our button clicked, maybe I want to say println user clicked the button. So this gives our registration. So we're actually attaching information to the button. And what's really nice about this gives us a nice separation so that we don't have to make a custom button to do custom functionality. Because before this pattern, what people would typically do is they have a button defined in their library, and they make a subclass of it that has a handler function inside of it. So there might be a abstract function called onClick inside button. And so the old version of this would be you create the button. Let me actually just put this up here at the top here real quick. Blah, 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 blah. So old version of buttons. So we might have something like a class old button. And I'm going to call him an abstract class old button. And then he has an abstract function onClick. And then other stuff to handle, to interpret user interaction. And then maybe I'd have to define explicitly my own buttons here. So class my button one implements button or old button. And then in here, I would override that onClick to say println user clicked the button. And that's kind of a disappointing functionality. I mean, but this made sense early on with early object-oriented user interface toolkits, because people were thinking, oh yeah, we just extend everything to change our functionality, and this worked. And the problem, of course, though, is that now we have to have a whole bunch of anytime we want a button, we have to create a subclass for it. Instead, what the observer pattern lets us do is have one button and just attach that onClick logic to it. And that's much more flexible, especially if you get a whole bunch of different things that you have to override in the button. Maybe you want to override how to draw a border on the button. Maybe you want to override the way the button displays the click. Maybe it has like a little ripple effect or something. Instead of having to override for all possible combinations of those things, we can just attach functionality to it. So in this case, we're using the observer pattern to attach the function of what to do when it's clicked. So down here, this allows us to do that attaching. I'm going to go ahead and run it. And boom, 3 seconds later, user clicked the button. Ta-da! Worked really well. So, we're assuming that the user had actually interacted with the button. But this is basically the code of how we attached that listening functionality. Okay, questions so far? So let's tweak this a little bit. Instead of using an interface for this, what we can do is we can use lambdas for this. And let's take a look at I'm going to rename this one to be button one. Let's create a button two. And actually, no, I want to do, I think I can just do this in the main for right now for what I'm trying to do. So we've created our button one there. Let's try saying button dot add button click listener, floop, and then put our println in here. Now what's happening with this is if we take a look at our onClick, our button click listener here, we have a single function. This is often called a single abstract method or a SAM. And when you have just a single abstract method in an interface, we call the interface a SAM interface. because it only has a single abstract method inside of it. And these are special cases. These types of special cases are ones that we can use lambdas for to implement these. Now at this point, it doesn't quite work because you'll see that it says we want a button click listener object, but we're passing in a lambda, a functional type. We can make a slight change to this interface up here. By putting the word fun in front of it, we're explicitly saying treat this as a functional interface. So we can define this as though it's the same as a functional type. So this is basically the equivalent of something kind of like this. It's basically equivalent to that. And so you'll notice now at the bottom here, this works perfectly well because we've now told Kotlin to treat that interface as though it were a functional type. And boom, now we can specify the lambda there perfectly well. And up here, of course, it gives the option to convert to lambda because you don't have to be as verbose on this anymore. But I'm going to keep the verboseness there. This only works for functional interfaces. I think I've done this with non-functional interfaces, but right now it's forcing me to do it this way. But I'm for some reason I'm thinking that I didn't have to do this all the time. Right now it's requiring me to. So, but this gives us that single abstract method interface. I can't do this if there are multiple functions. You'll notice that fun interface will not work here because you have to have just that one abstract method. Now you can have default functions. So if you had some helper stuff that you wanted people to be able to call, you can go ahead and have those in there, but you can only have a single abstract method inside that interface. And then that lets you, boom, do your add button listener, treating that exactly as a lambda. And that's much nicer. Questions so far? Okay, so the next thing we could do is we could just be explicit with this on the button itself. So we could actually have, instead of using that functional interface, we could specify this as a list of functional types. Bloop, 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 just like that. Functional types are just like any other type in Kotlin. You can use it inside of a generic like that. You can use it as the type of a variable, whatever. But now, of course, these listeners have to be changed because it's not compatible. Do that and boom. And we'll notice how it.buttonClicked is not going to work right. We could change this to it.invoke because that's what the functional type allows us to have. But because invoke is an operator, and in this case it is not null, we can just say it paren paren, just like that. So we're taking the function that's stored in this list and calling it as a function directly. Of course, you don't have to call it. You could say something like that, and that's, I'll just put it here, all of these are equivalent ways to call the listeners. Boom, just kind of like that. Make some sense? Any questions? Just keep in mind the only time you ever have to call invoke is if the parameter, the receiver for it is nullable. Then you don't have a choice. Excuse me. Okay, so that is another approach at the observer pattern. Notice how we don't have that interface anymore. We just have this functional type here that it, whoops, where did the, oh no, that's right. We just have this functional type here, which now doesn't have a name. So adding this listener, we're just saying it can be anything that implements that is providing a function that has no parameters and doesn't return a value. So there's a little difference in this. This one restricts it to objects that actually implement button click listener. This one, you can just pass in any old function you want. So if we had a class handlers, and inside here, he has a fun handle button click. Note that the signature of this guy takes no parameters and doesn't return a value. Well, I mean, unit is what's coming back. Then I can say println button was clicked, yay, something like that. So if I have this handlers thing here, I could do something kind of like val, handlers equals handlers. So I have this object sitting there. I could say button dot add button click listener handlers colon colon what did I call it? Handle button click. There we go. So now I'm using a function reference to pass that function in, and we'll notice that the function matches that functional type. Boom, just like that. And so now if I run this, I'm going to end up getting well, for this button, I will get, oh, it's the same button, so I should get 3 reports. After 3 seconds, boom, 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 ta-da, and that works just fine. So the functional types themselves are more flexible because I don't have to have an object that is forced into the interface type. All we have to do is match the signature of the function that we're using to be able to make that work. And that signature can be just an inline lambda. So in this case, the lambda has to match that functional type, or we can pass in a function there. Boom. Or in the case of this first button up here, wait a second, what did I do? Oh, I made it a functional interface. That's why this first, I didn't create a second button. So I really want to create a second button here just to use that. And we'll make this be button 2. And I'm going to comment out these guys. Let's go ahead and try running that. We should see that yay one come up again after 3 seconds. There we go. Why is he coming up 3 times? Oh, because I'm calling it 3 times. Yeah, that would make sense. I was thinking, wow, is it somehow calling the old button that or actually adding those 3 listeners? But no, it's actually, I explicitly printed these out 3 times. So this is a more flexible way to do it. The functional type is a much more comfortable way to do things. Okay, any questions on that? So that's pretty much the base stuff I like to talk about. The observer pattern is, how you have this separation. You don't create subclasses to do things, you attach things. And this also applies to functions. You can think of the observer pattern in a functional point as well. So basically observable functions. And all these guys are higher order functions which you'll recall can take a function as a parameter or return a function. In this case, we're going to limit the thought to function parameters. And we're going to limit the thought to tell me when something happens. Think about higher order functions for a moment. Higher order functions are super, super general idea. It's just a function that takes other function as a parameter or a function that returns a function. That's super useful for all sorts of type of work. And a bunch of different patterns can be implemented using that. When we're saying, I'm using the observer pattern, you are expressing a certain intent. And your intent here is, hey, guy I'm talking to, tell me when something interesting happens. And that's where you're really thinking in terms of observer, and you're doing something much more specific than just any old higher order function. So you're adding a lot of information for the reader if you mention the word observer when you're defining your function. So if I defined a function here that said create user interface, and inside here, maybe I pass some data in there that's, the initial, I don't know, a user object. And I defined a person, so I'll just go ahead and use that. So you're defining some kind of person that you want to display on there, but you also want to say when the user changes data, let's do something with that user. So I'm going to have a person coming in and then have a unit. And so what I'm writing here is something very similar to what you do in a framework called Jetpack Compose, which is currently the user interface framework for the preferred user interface framework for Android. And in this particular case with Compose, the functions you're defining are defining a tree of user interface components. So inside of here, I'd put some code that would actually say, hey, create some text fields to represent the information. And when the user enters information, call this data changed function. So I'll say create text fields, attach data changed to fields to catch text changes. And this is, a little oversimplified, but really what I'm doing is this function here is setting us up as kind of an observable itself. So we're saying that I want to observe what this function is doing, either directly or indirectly. With Compose, it's an indirect thing. It creates this tree of nodes, which the system renders for you. And then when the user interacts, it's going to call this data changed function. And the idea is you'll go ahead and change your data, and it'll automatically call create UI again. Now, depending on the framework, it might not have that automatic capability. You might have to explicitly call create UI again. But Compose is kind of cool because you set this up, it displays your user on the screen, and then when things happen, data changed is called, and the caller of this just changes data, and poof, create UI is called again. It's really nifty. So for those of you who haven't taken my Android class, take my Android class. You're going to love it. It's really cool stuff. But this is a way that I would call this an observable function. The concept in my head is that I want to know when something happens. And so as part of this function, I'm passing in an observer. So note that this implementation is incredibly different than what I talked about earlier. Earlier, it was much more of a traditional thing where I have a class, I have listeners that I'm attaching to it, boom. The listeners could be instances of some classes, or instances of interfaces, or they could be functions being passed in to be called. But the whole point here is really that I'm communicating to you how I'm thinking about the problem. And that is gold for a maintainer. If a maintainer can get into your head in any way, it's going to make their job a lot more effective, and easier. But most importantly, I want to make sure that it's an effective job for them. I want them to do the right thing, because if they don't really know what I was thinking, they may end up putting their changes in the wrong place, or they may interpret bugs that they're having in different ways that it might not be appropriate. Cool. Any questions on any of that? So we're starting to see Kotlin being used in more realistic examples at this point. I'm still going to give you a lot of little, silly, example problems and things like that. But I want to try to show you some more realistic scenarios as well along the way, so that the course will be a little bit more. You'll see the language in use in ways it's intended to be used. Okay. Any questions on anything here? Any questions on exam prep? Okay, I won't be talking about this observer stuff, that won't be on the exam, but anything before the break will be. Okay, so I will call it there, and wish you all a wonderful night. And study hard, do great on the exam next week. Again, if you have questions, after you've been doing some studying, feel free to pop into the office hours, and we can chat about them. Otherwise, I will. Well, I won't be talking to you directly for the exam, but you will have the exam up in Canvas to have some wonderful fun with. Have a great night.